Hello, I'm Alan Bowling from the Department of Mechanical and Aerospace Engineering at the University of Texas at Arlington. This presentation looks at part 2 of looking at 2D vectors in engineering. So let's get started. So recall our real-world problem was to move from point A to point B over here and to investigate the distances involved in making that journey. So we translated that into mathematical language. We did it graphically. And here we did it using pure math. So now we want to go completely into the math world, and we're going to do that next. So here we are in the math world. So you see the map is gone. So we want to investigate two key properties of a 2D vector. The first one is called the magnitude, or length. And that is represented by this symbol. And it's equal to the square root of the sum of the squares of its components. So it looks like that. And PAB actually defines that length from point A to point B as we say, as the crow flies. The direction of PAB is obtained by dividing PAB by its magnitude. And when we divide PAB by its magnitude, we get a unit vector. And it looks something like this. Hat plus y over the square root of x squared plus y squared e. Now this little hat thing, that indicates a unit vector. And you notice that this hat also shows up here and here. So we also consider those directions to be unit vectors. But the nice thing about a unit vector is that the magnitude of a unit vector is equal to 1. But even better than that, even more interesting than that, is the fact that if we look at this graphical picture here, and if you took your geometry, you know that this distance is less than this distance, x plus y, and x plus y is the distance you walk along the street. Okay? So, another thing you might notice in the math world is that I can switch the order of this addition. So I can do this, I can switch this around and go from here and go up to there, and I get the same answer. Now you know that in the real world you couldn't walk that. You can't walk this path. So in the real world, you know, this path here doesn't work because there's no streets there. But in the math world, I can switch it around and do that. So let's explore this idea of magnitude and length a little bit further. So what we said was that the length of PA to B was equal to square root of x squared plus y squared, which are the distances along the street. So let's give these some values. We'll say x equals 3 inches, feet, meters, miles, whichever you like, but they're units of distance. And we'll say y is equal to 4 miles, feet, whatever you want. And we'll just plug this in. So 3 squared is 9 plus 4 squared is 16. And that gives us the square root of 25, which is equal to 5. So if we look at the distance involved in walking over the street, that's x plus y equals 3 plus 4, which equals 7. So you see that it is longer to walk along the street than it is to fly straight over as the crow flies. But the interesting thing is that this distance, 3, and this distance, 4, are easy to get because we can just walk along the street and measure them. But this distance here is hard to get because you'd have to go through people's yards and climb fences and this kind of thing. It's hard to measure that. So we can use our mathematics to take these easy measurements, 3 and 4, and find the hard measurement, which is 5, which is harder to get. And that's one of the key things we can do with vectors. Okay, let's take this idea of distances a little bit farther. So let's look at this again. We had our point A here, and we had our point B here. And now we want to add a different destination. Let's say we want to get to point D. So let's put our directions back in, and again we assume that all these streets are perfectly straight. And we already have this vector from PA to B. And we just need to add to it this guy. So I'm going to make a distance here, which I'm going to call, this distance is going to be Z. So we already have PA to B as X in the north direction plus Y in the east direction. And now we need to define B to D as being minus Z in the north direction because we're going down instead of up. And we're going in the negative north direction. And we can represent this, the distance from A to D, as the vector addition of A to B plus B to D. And if we plug all this in, we get X to the north, Y in the east, minus Z in the north. And we can combine the like terms to get X, Z in the north, plus Y in the east direction. So that's mathematically how we look at it. Let's look at it graphically. So we already have PA to B. Let's do this. This gives us P, B to D. And again, we put the tail of one on the head of the other vector. And so we can draw this vector in between. And we'll call this P, A to D. But even more interesting, we can look at the distance here. So our original path was to go all the way up here, all over there, and down to here. That would be our original path, and that was x, y, plus z is what that looks like in math. However, the going straight as the crow flies, if we could fly over this and just go straight from A to D, the distance would be taken from here. So it gives us x minus z squared plus y squared would be the distance along from straight from A to D. Now just looking at this, you can see that this distance here is going to be much less than going all the way up here, all the way over here, and all the way down to there. So we can use our math to calculate this distance, which is hard to find because we have to go through lawns and people's yards and everything, and compare it to this distance, which is going to be much greater. And if the difference is really, if this is much, much greater than this distance, then you probably think, well, we might want to pick a different route because that's way far to go when there's probably a shorter way to get there. So that's another way to use 2D vectors. So in summary, we learned about two key properties of a 2D vector, its magnitude and its direction. And we were able to use especially the magnitude information to investigate the distance between different points on the map, which we could use to think about the shortest way to travel to our destination. So thank you for watching.